Hi guys, hope you all are doing well, and here we are with another video. Probably this would be the second last video for our topic. In case you haven't subscribed to the channel, please go ahead and subscribe the channel, and in case if you do not follow any of my topics, just I would request you to go back one or two videos behind and you will get the link. So I would suggest you that you follow the playlist and not just isolated video. So what are we going to do today? We are going to discuss two things. We are going to discuss Wien's displacement law, Wien's displacement law, and we are going to discuss Prevost's theory of heat exchange. Prevost's theory of heat exchange. So these are the two things we are going to discuss today. Let's see how it works, and in the next video we will be ending kinetic theory, and maybe we can start with another topic going forward. Yes, the theoretical part for kinetic theory would be, we will be finishing with the last two topics, that's Stephen Boltzmann's law and Kirchhoff's law. So today we will be starting with Wien's displacement law first. Now if you have been following me, you would have got that this diagram we had done in the previous video. In case you are not, I would request just one video before you will be having a great detailed discussion about this. So Pringsham and Lammer, these were the two guys who found out the relation between the emissive power and the wavelength, and if you keep on increasing the temperature T1, T2, T3, then the peak of this graph actually shifts backward. So this is lambda max 1, lambda max 2, lambda max 3. Now lambda max does not indicate maximum wavelength. Maximum wavelength would be at the extreme end of this axis. But lambda max is that the wavelength for which the intensity is maximum. Wavelength for which the intensity is maximum. Because of this peak, this wavelength has the maximum intensity. Because of this peak, this wavelength has the maximum intensity. Because of this peak, this wavelength has the maximum intensity. It's clearly visible that wavelength and the temperature is getting an inverse relationship. So if you have understood this graph, then Wien's displacement law is true. So this is Wien's displacement law. The wavelength for which the intensity of radiation is maximum, that is lambda max, depends inversely. So depends inversely on the absolute temperature. So on the absolute temperature. So lambda max depends inversely on the absolute temperature. So I have written this. Lambda max is inversely proportional to 1 upon T. If you want to remove this proportionality sign, you put an equal to sign and you multiply by a constant. This constant is what is called as the Wien's constant. Wien's constant. And T is temperature in Kelvin. This has to be in Kelvin. B is Wien's constant, and Wien's constant is, value for Wien's constant is 2.897 into 10 raised to minus 3 meter Kelvin. This is meter Kelvin. M should be small, K should be capital. So this was Wien's displacement law. That is nothing much, very easy. And Wien's displacement law is used in finding temperature of the stars by studying the wavelength emitted by them. So if you see, like suppose from Earth we are seeing a star, and this star is emitting radiations, and if you understand the radiation and find out the wavelength, let's say lambda 1 is the minimum wavelength, lambda 2 is the maximum wavelength in which it is emitting the spectrum. And so let's say, okay, suppose this is one of the wavelength which has the maximum intensity. So if I have lambda max, I can put it over here, and B is a constant which we know. So we can easily find out T is equal to B upon lambda max. So finding out lambda and B can fetch me what the temperature of that star is, what the temperature of that body is. So Wien's displacement law is used in order to study the temperature in order to find out the temperature of the star by studying the wavelength emitted by them. Okay. So this is all about Wien's displacement law. Now let's go to something called as Prevost's theory of heat exchange. Before going ahead, I would like to explain this first. So let's say we have this a teacup, and this teacup is pretty hot. Okay, let's say the tea is hot. Let's say the temperature of the tea is 80 degrees Celsius and the surrounding temperature is 20 degrees Celsius. And maybe we can also have this ice cold bottle. If you have been following my initial videos, this example was common. Let's say suppose there is ice in this. Okay, and I'll just change this color. Okay, so this is ice, and let's say the temperature of the ice is 0 degrees Celsius and the surrounding temperature is 20 degrees Celsius. Now, so what happens here is, okay, let's just consider the case of just this body, the T. Now, if you consider this, what is going to happen is, okay, as there is a difference in temperature, you will find out that heat is going to flow from the higher temperature region to a lower temperature region. That is, the direction of the Q is from the teacup to the surrounding. And the reason being, there is a difference in temperature. So Prevost theory says that at any given temperature, a body will absorb as well as emit. So this teacup is going to emit as well, it is going to absorb as well. Even though its temperature is 80 and the surrounding temperature is 20, still it is going to absorb as well as it is going to emit as well. But the rate of emission and the rate of absorption may be different. And that's the reason why it is going to emit more and absorb less. That's why its temperature is going to go down, and after a large time you will find out that they both will come at the same temperature, like 20 degree surrounding and 20 degree ka T. And that point we'll call as thermal equilibrium. That point is called as the thermal equilibrium, when the temperature of the two bodies become equal. Okay. Now the Prevost theory says, the first point says that at any given temperature a body emits as well as absorbs, both ways. Now what happens, okay, the rate of absorption and rate of emission may be different. Maybe a body might be absorbing more or emitting more, and vice versa. So in case if you see about these bodies like this one, then you will find out, okay, in this case the surrounding is at a higher temperature. The surrounding is at a higher temperature and the body is at a lower temperature. So heat is going to go flow from higher temperature region to a lower temperature region, that is from the surrounding to the bottle. But Prevost theory says that even though this is at a 0 degree Celsius, but it is still absorbing as well as emitting. So it is also emitting radiation and it is also absorbing radiation. But the rate of emission, and rate of absorption may be different. And this rate of absorption and emission will become equal only when they are in thermal equilibrium. So when the bottle comes at 20 degrees Celsius, which is the surrounding temperature, the rate of absorption and the rate of emission will become equal. And for this teacup as well, if the tea comes at 20 degrees Celsius, that is thermal equilibrium, then we can say the rate of absorption and rate of emission becomes equal. So it does not mean that it has stopped emitting, it does not mean it is stopped absorption, but the only thing is that they both have stopped, absorption and emission has become equal. Okay, so this is these are the 3 points which I have just recently discussed now. Prevost theory of heat exchange: any body at any given temperature emits as well as absorbs heat. So however high the temperature is, however low the temperature is, it doesn't matter, it will emit as well as absorb. Second point is the rate of absorption and the rate of emission may be different. So rate of absorption and emission may be different for different temperatures, but they can be equal. When that is a thermal equilibrium. So when the body is in thermal equilibrium, then the rate of absorption and the rate of emission would be same. So on thermal equilibrium, the amount of heat emitted and the amount of heat absorbed will remain same. Now here is the point where most of the confusion begins. First is that rate of emission, the amount it is emitting. So if I just copy this diagram, okay, so let's paste it over here. Okay, Now if you see, the rate of emission, the amount of energy it is emitting will depend on the surface area of the cup. So it depends on area. Larger the area, the larger would be the emission rate. That's why we see that larger area emits more and it becomes cooler faster. Okay, so if you have um, let's say some hot water in a bottle, and if you have a tea and if you just spill it over on the ground, then you will find out it will become cooler faster than when it would have been if it would have been on a cup. Okay, so this is one. Then it also depends on the nature of the body, and now when I say nature, I mean to say whether it is rough or whether it is polished. So it also depends on nature. Third is time. How much time we are considering this experiment to be done. And the most important, the most confusing part is the rate of emission depends on the temperature of the body, and it does not depend on the temperature of the surrounding. It does not depend on the temperature of the surrounding. So rate of emission does not depend on the surrounding. It depends on the temperature of the body only. And now the last point and the fifth point is the rate of absorption depends on the surface area. That same, nature of the body, that same, time is same, but the rate of absorption depends on the temperature of the surrounding and not on the temperature of the body. This is a very important difference we are understanding here. So the tea cup is absorbing as well as emitting as well, but the emission depends on the temperature of the body. But the absorption depends on the temperature of the surrounding. So if the temperature of the surrounding is higher, the absorption rate would be higher for the teacup. Okay, so this is all about Prevost theory, and we will be using this Prevost theory in order to prove Kirchhoff's law. And in case you haven't taken the screenshot, you can just go ahead and take a screenshot, magnify, and make your own notes. And in case if you haven't subscribed my channel up to as of now, we also have done Wien's displacement law today, so you can just have a go at it. You can take a screenshot now, and you can take a screenshot now. And in case you haven't subscribed the channel, just subscribe the channel and follow the videos from the start so that you can understand it well. Thank you so much. Bye.